kinetic energies of a planet in elliptical orbit around Sun at positions A, B, and C are K, KB, and KC respectively. AC is the major axis. SB is perpendicular to AC. SB is perpendicular to AC at the position of Sun as shown in the figure. Then these are the options. Okay, K is less than KB is less than KC. Then K is greater than KB is greater than KC. KB is less than KA is less than KC, and KB is less than greater than KA is greater than KC. Which one will be correct? So see, we have seen angular momentum is constant. Okay, so mass of planet multiplied by V multiplied by R is constant. So considering mass is already a constant, we can say the product of V and R is constant. So if V is more, sorry, if R is more, V will be less. If R is less, V will be more. So closer is the planet to the Sun, higher will be its velocity, and therefore higher will be its kinetic energy. Okay, so Indra is saying option 2, option B. So K is greater than KB is greater than KC. Right, exactly. So since it is closest at position A, its velocity will be highest at position A. Okay, and it will be lesser at B and even lesser at position C. So this is correct. Very good. Let's see this question. Planet moving along an elliptical orbit is closest to Sun at distance r1 and farthest away at distance r2. If v1 and v2 are the linear velocities at these points respectively, then the ratio of v1 by v2 is. So we have just seen that v times r is a constant. Okay, so we can say v is equal to what? Some constant divided by r. So v is inversely proportional to r, and therefore v1 by v2 will be equal to what? R2 by r1, right? Since it is inverse proportion, v1 by v2 will be equal to r2 divided by r1. Okay, next question. The figure shows elliptical orbit of a planet M about the Sun. The shaded area SCD, so SCD is twice the shaded area SAB. So this area is twice compared to this area. Okay, twice of this area. T1 is the time for the planet to move from C to D. T1 is the time to move from here to here, and T2 is the time to move from A to B, A to B. Then, very simple, area is double, that means time will be double. Okay, because area, so because the line joining Sun to the planet sweeps out equal areas in equal intervals of time. So if area is double, time would be double. Right, so option B is the answer. Okay, right. So this was very simple. Next one. The period of revolution of planet A around Sun is 8 times that of B. The distance of A from the Sun is how many times greater than B, that of B from the Sun? So we know T square is proportional to R cube, right? T square is directly proportional to average distance cube. So we can say T1 by T2 square is equal to R1 by R2, R1 divided by R2 cube. Okay, and it's given that T1 is 8 times that of T2. Period of revolution of planet A is 8 times that of B. Okay, so this is 8 times T2 upon T2 square. So T2 and T2 gets cancelled. So it is 64. Okay, so this is equal to 64, and it is R1 upon R2 raised to 3. So we know that 64 is 4 cube, right? 4 times 4 times 4. Okay. So we have R1 upon R2 raised to 3 is equal to 4 raised to 3. Okay. So this is equal to what? 4 raised to 3. Okay. So therefore R1 upon R2 is equal to 4. So R1 is 4 times more. Option A. Okay, there have been lot of questions based upon Kepler's laws, which are very easy. Okay. The distance of two planets from Sun are 10 raised to 13 meters and 10 raised to 12 meters respectively. The ratio of time periods of planets is, again, this is very simple. So T1 divided by T2 raised to 2 is equal to R1 divided by R2 raised to 3. Okay, so this is 10 raised to 13 upon 10 raised to 12. R1 is 10 raised to 13 and R2 is 10 raised to 12 raised to 3. So 10 cube, or we can say it is 1000. Okay, so T1 upon T2 is equal to square is equal to 1000. So T1 upon T2 equals to what? Square root of 1000. And 1000 can be written as 100 times 10. So square root of 100 is 10. So this is equal to 10 root 10. Okay, option B. Right? Okay. So again, this is similar question. Next question. The planet is moving in an elliptical orbit around Sun. If T, V, E, and L stand respectively for its kinetic energy, gravitational potential energy, total energy, and magnitude of angular momentum about the center of the force, which of the following is correct? T is conserved, that means total energy is conserved. Okay. No, T is not total energy, it's kinetic energy. V is always positive, E is always negative, and L is conserved, but direction of vector L changes continuously. So we haven't studied about other things, but we know that L is conserved, right? So we'll study about other things, that means kinetic energy, potential energy, etc., etc. But we already know that angular momentum is conserved, right? So option D is the answer. Okay. Next question. Two sorry, two astronauts are floating in gravitational free space after having lost contact with their spaceship. So there are two astronauts, they are floating in gravitation free space. So the two will move towards each other, move away from each other, will become stationary, keep floating at the same distance between them. So what is true? Yes. Option A, move towards each other. Right. So space is gravitation free means they are far away from any other mass in the universe. But they have their own masses, right? And because of their own masses, they will get attracted towards each other. So option A is correct. Good, Indira. Okay. The next question. Two spheres of masses small m and capital M are situated in air and the gravitational force between them is F. The space around the masses is now filled with liquid of specific gravity 3. The gravitational force will now be. So what will happen? Okay, two spheres of masses m and capital M are situated in air and gravitational force between them is F. The space around them is now filled with the liquid of specific gravity 3. Okay, so the gravitational force will now be, yes, option B. Okay, why is it so? Gravitational force does not depend on the medium. Okay, it is independent of medium, right? Next question. If gravitational force between two objects were proportional to 1 divided by r and not as 1 upon r square, where r is the distance between them, then the particle in circular path under such a force would have its orbital speed v proportional to. Okay, so now let's suppose Earth moves around Sun in circular orbit. So it's the gravitational force due to Sun which provides for the centripetal force, right? So this is Sun. It's the gravitational force which provides for the centripetal force, and therefore we can say FCP is equal to gravitational force. And now what they are saying is, suppose the force, gravitational force, was inversely proportional to r, okay, and not to r square, then the speed is proportional to what? Okay, so let's suppose gravitational force is some constant divided by r. Okay, so now what is FCP? It is mv square upon r. So mv square upon r is some constant divided by r, because gravitational force, it's given that it is inversely proportional to r only. So this r and r will get cancelled. Mass of the planet is a constant. So v square is equal to this c divided by m. So this is another constant, right? So therefore v is constant, or we can say, yeah, it is independent of r. Option B is the answer. Let us see next question. The Earth mass is 6 multiplied by 10 raised to 24 kg, revolves around the Sun with an angular velocity 2 multiplied by 10 raised to minus 7 radians per second in circular orbit of radius 1.5 multiplied by 10 raised to 8 kilometers. The force exerted by Sun on the Earth in Newton is. So what is given? Mass is given, angular velocity is given, and radius is given. So gravitational force provides for the centripetal force. So we have this formula for centripetal force. F is equal to mr omega square, right? It is mv square upon r, okay, or we can say it is mr omega square, another formula for centripetal force. So let's substitute values. So values are 6 multiplied by 10 raised to 24 multiplied by r is 2 multiplied by 10 raised to minus 7. No, it's not r. This is angular velocity. R is 1.5 multiplied by 10 raised to 8 kilometers. So we have to convert it into meters. So 10 raised to 8 multiplied by 10 raised to 3, 10 raised to 11 will come. Okay, multiplied by 2 into 10 raised to minus 7, and we have square of that. Okay, so what do we get? So it is 6 times 1.5 multiplied by 4 multiplied by 10 raised to how much? 24 plus 11. 24 plus 11 is 35 minus 14. Okay, minus 7 raised to 2. Okay, so it is 1.5 multiplied by 4 is 6. 6 times 6 is 36. 36 multiplied by 10 raised to 21 would be the answer. Option A, right? This is from 2014. Dependence of intensity of gravitational field E of Earth with distance r from the center of Earth is correctly represented by. So gravitational field is nothing but what? Acceleration due to gravity. Okay, tell me which one is correct. I have seen this, no? It's option B. Right, it's option B. Okay, so this is simple question. Next one, which one of the following plots? Okay, so yeah, others, is there a problem in this question? No, right, Sanjay? Okay, good. Then next question, which one of the following plots represents the variation of gravitational field on a particle with distance r due to a thin spherical shell? Now this is different. It is thin spherical shell. Okay, gravitational field due to thin spherical shell of radius r. Small r is measured from the center of spherical shell. So we know this. Okay, for a spherical shell or a spherical shell, if you keep a mass inside shell, okay, what is gravitational field? It is gravitational force per unit mass. So let's suppose mass of the shell is capital M. Okay, if you keep other mass inside the shell, what will be the gravitational force on that mass due to the shell? It's zero. Okay, therefore the gravitational field inside the shell is also zero. Till what? Till the distance r. Okay, till you reach till the surface of the shell, right? So when r is smaller than r, E is equal to 0, the gravitational field is equal to 0. When you go outside of the shell, okay, then the gravitational force is equal to what? It is just gmm upon r square. So it is inversely proportional to r square. Okay, therefore the gravitational field, which is force per unit mass, will be just gm upon r square. Okay, therefore E, which is equal to force upon mass, is just gm upon r square, and 1 upon r square is like this. Okay, so which one is correct? Here field is denoted by F. Okay, sorry, it's not E, they are denoting it by F. So let's call this F as the gravitational force, and field F is equal to what? This force divided by mass. Okay. So still it doesn't matter, it's option B. Yes, no. Okay, till the distance from center of the shell is less than r, the force on any mass which is kept inside the shell will be equal to 0. Okay, so therefore the gravitational field is 0. Okay, till distance r. After that it is equal to gm upon r square. Okay, gm upon gm divided by capital R square. Okay, this will be the maximum value, and then it falls as inversely to the r square. Okay, so it is gm upon r square. So therefore it's option B. Then let's see next question. A body of weight 72 Newton moves from surface of the earth at height half of the radius of earth, then the gravitational force exerted on it will be. So gravitational force, okay, will be equal to what? At height h is equal to mass multiplied by acceleration due to gravity at that height. Now question is, which formula for acceleration due to gravity should we use? We have this formula, g multiplied by r upon r plus h square, and we have another formula, g multiplied by 1 minus twice h divided by r. So which one should we use in this question? Okay, height is equal to, given is height is equal to half of the radius of earth. First or second, tell me. Second formula is approximate. Okay, we can use it till the time h is very small compared to r. Okay, what do I mean by very small? Max to max 10%. Okay, and here it is half. Okay, h is equal to r upon 2. So we cannot use this second formula. We have to use the first one, right? Okay. So what is weight of object? It is gravitational force due to earth on an object. Okay, so W is equal to mg. This is on earth's surface, and for height h, the weight will be equal to what? Weight at height h will be equal to mass multiplied by acceleration due to gravity at that height. Okay, so m into gh, which is m multiplied by, we'll use this formula. Okay, g multiplied by r upon r plus h whole square. Okay, and what is mg? It is weight on earth's surface. So w, let's call it w. So let's put h, so it is r upon r plus r by 2 square, right? So it is 3 by 2 r in denominator, r gets cancelled, it is 3 by 2 in denominator, so we can move that 2 into the numerator. So 2 by 3 square, which is 4 by 9, right? 4 by 9, this is my 9, okay? It's not g, this is 9, multiplied by weight. And how much is weight? It is 72 newtons, 72, okay? So 8 nines are 72, so we have 8 times 4, 32 newton is the answer. Oh, you calculated, very good. Okay, it's option B, good. If the mass of sun were 10 times smaller and the universal gravitational constant were 10 times larger in magnitude, okay, which of the following is not correct? Option A, raindrops will fall faster. Option B, walking on ground would become more difficult. Option C, time period of simple pendulum on earth would decrease. And option D, G on earth will not change. Can you tell me? Mass of sun were 10 times smaller. Okay, so mass of sun is 10 times smaller, and G is 10 times larger. So let's suppose G dash is equal to 10 times of I'm sorry, G. Okay, and mass of sun is equal to 1/10 of the current mass of sun. So ms prime is equal to ms divided by 10. So raindrops will fall faster. Okay, will this happen? Yes, it will happen, because what is acceleration due to gravity? It is gm upon r square. Now you have, if g changes, okay, if capital G changes, what will happen? Small g will also change. Now mass of earth is not changing, radius of earth is not changing, okay, so they are given to be constants. So it is g prime upon multiplied by m divided by r square. Okay, So now see, g prime is 10 times of g. So that means acceleration due to gravity will become 10 times. Okay, 10 times larger. So raindrops will fall faster because Earth is attracting them with greater magnitude, 10 times greater magnitude, right? So V, which is square root of 2gh, right? If they are falling from some height h, square root of 2gh. So since g is increasing, V will increase. So this is true. Then walking on ground would become more difficult. This is also true because acceleration due to gravity has increased. So we have to exert more force against Earth's gravitational pull, right? So this will become more difficult. It is true. Time period of simple pendulum on Earth would decrease. So what is time period of simple pendulum? T is equal to 2 pi square root of L upon G. Okay. So it is inversely proportional to root G. So if G increases, T decreases, right? If G increases, T decreases. So this is true, this is true, this is true. Which is not true? This is not true, right? And we can see that G on Earth will not change. They are saying G will not change, small g, acceleration due to gravity. And okay, so it will change, right? So this is the answer. Let's see next question. A spherical planet has mass m suffix p and diameter d suffix p. A particle of mass m falling freely near the surface of this planet will experience an acceleration due to gravity equal to. So very simple question, right? So we just have to remember g equals to g times m upon r square. So for that planet, what will be g? Gp will be g into mp upon rp square. Okay, radius of that planet square. Okay, right? So here diameter is given, which is radius divided by 2. So we can substitute that. So we get g times mp, mass of the planet, divided by diameter. Radius is diameter upon 2. So dp by 2 square. Okay, and that 2 square will go to the numerator. So you can say it is 4 times g multiplied by mass of the planet upon dp square. Okay, so this is it's option A, right? This is very simple. Next question is, imagine a new planet having the same density as that of Earth, but it is 3 times bigger than the Earth in size. Okay, let's imagine a new planet. Okay, same density as that of Earth, and it is 3 times bigger than that of Earth. If the acceleration due to gravity on the surface of Earth is g and that of the surface of new planet is g dash, then tell me, see, if density is coming, which formula should we use? G is equal to 4 by 3 pi r rho g. Okay, so I wrote this formula for Earth. For that planet, it will be g dash equals to 4 by 3 pi r dash rho dash. Okay, this g will not change. It is universal gravitational constant, right? So density of that planet is equal to density of Earth. Okay, so g for Earth is 4 by 3 pi r rho times g. So rho dash is equal to rho. It's given, but it is 3 times bigger. Okay, so r dash is equal to 3 times r, right? And therefore, you can say, you can write here 3 times r, it is 4 by 3 pi multiplied by 3 times r into rho into g. Rho dash is equal to rho. R dash is equal to 3 times r. And therefore, it is 3 times of g, right? It is equal to 3 times of g. Option D. Okay, so whenever density comes, okay, whenever density is involved, you have to use this formula. Okay, please remember this. Whenever density is there, use this formula. Okay. Next question. The density of a newly discovered planet. Again, a newly discovered planet. Okay. Planet is newly discovered. Is twice that of Earth. Acceleration due to gravity at the surface of the planet is equal to that of the surface of Earth. If the radius of Earth is r, the radius of the planet would be. Okay, so newly discovered planet. G dash is equal to G. This is given. Okay, so 4 by 3 density is involved. Which formula do we have to use? 4 by 3 pi r rho G. Okay, pi r rho multiplied by capital G. But it is for that planet, so let's put dash r dash rho dash. Okay, it's equal to density of, sorry, acceleration due to gravity of Earth. It is 4 by 3 pi r rho G. So 4 by 3 pi, 4 by 3 pi cancelled. G and G is cancelled. So what's given? Radius, sorry, density is given is twice that of Earth. Okay, so rho dash is equal to 2 times rho. Rho dash is equal to 2 times rho. So rho and rho is also cancelled, right? I will just put rho dash is equal to 2 times rho. So you get r dash is equal to what? R upon 2. Take the 2 on other side, right? So questions on gravitation. Most of the questions are very simple. The acceleration due to gravity on a planet A is 9 times the acceleration due to gravity on planet B. Okay. A man jumps to height 2 meters on surface of A. What is the height of jump by the same person on planet B? Yes, can you tell? So here, now same man, suppose same man jumps with same velocity, right, on both the planets. So till what height will he go? Okay, so acceleration on a planet A is 9 times the acceleration due to gravity on planet B. Okay, so we know that V square is equal to 2gh. Okay, so VA square is equal to 2 times GA HA. Okay, and we'll divide that by VB square, which is 2 times GB HB. Okay, but same man will jump with same velocity, right? So V square and V square is cancelled. We can write 2 times GAHA is equal to 2 times GBHB, right? Or GAHA is equal to GBHB. Okay, so right. So what will be the answer? So on planet A, it is 9 times. Man jumps to height of 2 meter on surface of A. So this is 2. HA is 2. Okay. And GA is 9 times of GB multiplied by 2 we have. Okay. So it is GB times HB. So this H and H, HB and HB gets cancelled. What did I do? Sorry. GB and GB gets cancelled. Okay. So HB is equal to what? 9 times of 2. That's 18 meters. Next question. What will be the formula of mass of Earth in terms of small g, r and g? This is very simple, right? So we just have to remember g is equal to gm upon r square. Okay, so what is asked? What is the formula for mass? So what is the formula? M is equal to g multiplied by r square divided by capital G. Okay, it is option B. The acceleration due to gravity g and mean density of Earth rho are related by which of the following relations? So we know that relation, okay, but they have asked about rho, not g. Okay, So we know that G is equal to 4 by 3 pi r rho G, right? And we want rho because in all options they have given rho. So take everything else on the other side. So rho is equal to, okay, 3 by 4 times G. Okay, if I take this on other side, it will become 3 by 4 times G divided by pi r capital G divided by pi r capital G, which is the which option? Option A, right? Option is answer. Okay, this is straightforward. All right. Next question. Radius of Earth is about 6,400 kilometers and that of Mars is 3,200 kilometers. The mass of Earth is about 10 times mass of Mars. Okay, so radius of Mars Mars is equal to what? Half of the radius of Earth, r upon 2 we can say. And mass of Earth is about 10 times mass of Mars. Okay, that means mass of the Mars is equal to mass of Earth divided by 10 because Earth's mass is 10 times. Then an object weighs 200 Newton on the surface of Earth. Its weight on the surface of Mars will be. So what we have to do? We have to find out the acceleration due to gravity on surface of Mars. Okay, so let's do that. So G on Mars surface will be equal to G times mass of the Mars divided by radius of Mars square. Okay, and that is G times what is mass of Mars? It is mass of Earth divided by 10, m upon 10 divided by, and what is radius of Mars? It is radius of Earth upon 2. So it is r upon 2 square we have. Okay, so it is 2 square is 4. It will go to the numerator. So you have 4 upon 10 times gm upon r square. Okay, that is 4 by 10 or 2 by 5 times the acceleration due to gravity due to the earth. This is acceleration due to gravity due to earth. Okay, so it is 2 by 5 times g, and therefore weight on Mars will be equal to what? 2 by 5 times weight on the earth. Okay, and what is weight on earth? It is 200 Newton. Okay, so 2 by 5 multiplied by 200. How much is that? 2 by 5 multiplied by 200. So 200 by 5 is 40. 40 times 2 is 80. So 80 is the answer. Got it? Oh, you solved it. Very good. Okay, correct. Option C. Okay, let's see next question. A body weighs 72 Newton on surface of Earth. What is gravitational force on it at the height equal to half of the radius of Earth? So this is repeated question, exactly repeated, right? So we have solved it. It is 32 Newton. I remember. Yes, no? The body weighs 200 Newton on surface of Earth. How much will it weight? Halfway down to the center of Earth. Okay. So for that we need to find acceleration due to gravity at depth d. And how much is d? It is r by 2 because they are asking how much will be its weight halfway down to the center of Earth. That means d is equal to r upon 2. So gd is equal to g multiplied by 1 minus d by r. And what is d by r? If you take r on other side, so d by r is 1 by 2. 1 minus 1 by 2 is 1 by 2. So it is g by 2 only. Okay. g by 2. And since acceleration due to gravity becomes half, weight becomes half because weight is m times g. Okay, so it is 100 newtons. Next one, the acceleration due to gravity at height 1 kilometer above the earth is same as a depth d below the surface of earth. Then how much is d? They are asking. So here it's only 1 kilometer, so we can use this formula. G at height h is equal to g multiplied by 1 minus twice h upon r. Okay, and they are saying same as depth d, so it's equal to gd. So what is gd? Gh is equal to, they are saying gh is equal to gd. So it is equal to what? G multiplied by 1 minus d upon r. So this g and g gets cancelled. Okay, after that it is 1 minus twice h upon r is equal to 1 minus d by r. So that is twice h upon r is equal to d by r. R gets cancelled. D is equal to 2 times h. Okay, so it is 2 kilometers, right? D is equal to 2 times h. H is equal to 1 kilometer. So D is equal to 2 kilometers. Okay, simple question. And this question has been repeated many times. Starting from center of Earth, having radius r, the variation of g, acceleration due to gravity, is shown by. Okay, sometimes they call it gravitational field. So it's same thing. What is the answer? It's option B. Okay, good. Then next question. The height at which weight of body becomes 1 by 16th is weight on the surface of Earth. So this is also simple. So what they mean is gh is equal to 1 by 16th of g. Okay, but we know gh is equal to g multiplied by what? Okay, because it becomes 1 by 16, so we have to use this formula. It will not happen for small heights, right? So r upon r plus h square. Okay, gh is g multiplied by r upon r plus h square. So it is 1 by 16th of g. G and g gets cancelled. Then we have to take square root. Okay, so r upon r plus h square is 1 by 16. That means r upon r plus h is equal to 1 by 4. That means r plus h is equal to 4r. Okay, so h is equal to what? 4r minus r, that is 3r. Then this is from mains 2010. Okay, and its answer is option 4, that is A. So it is repeated many times, repeated in many exams, this question. Okay, r is radius of earth, omega is its angular velocity, and gp is the value of g at poles. The effective value of g at the latitude lambda equals to 60 degrees is. So what is the effective value? G at latitude lambda. Okay, so latitude we denoted by phi, they are denoting it by lambda. So it is equal to what? G minus r omega square cos square phi, or they are calling it lambda, so let's call it lambda. Okay, so it is G at poles is equal to G, so we can write this as G at poles minus r omega square multiplied by cos of 60 degrees square. And how much is cos 60? 1 by 2, right? So it is 1 by 2 square, 1 by 4. Okay, so it is Gp minus what? 1 by 4 r omega square. Option A. Next question. If the rotational speed of Earth is increased then the weight of a body at the equator, what will happen? It will increase, decrease, becomes double, does not change. Tell me, G at equator is equal to what? G minus R omega square. If rotational speed is increased, what will happen to the weight? So we know that weight is equal to what? Weight of an object is gravitational force acting on the object, right? So if omega increases, then weight decreases. Good. This was simple. Next question. The acceleration due to gravity on Earth's surface at the poles is g, and angular velocity of the Earth about the axis passing through the pole is omega. An object is weighted at the equator and at height h above the poles by using spring balance. If the weights are found to be same, then h is. So, and they are giving h is very small compared to r. That means we can use gh is equal to which formula? G multiplied by 1 minus twice h upon r. And they are calling this is equal to what? G at equator. Okay. The weight of object is same means acceleration due to gravity is same. And what is G at equator? So G at equator, okay, I will write this as G minus G multiplied by twice h upon r is equal to G at equator is G minus r omega square. We know this. Okay. So this G and G will get cancelled out, right? Yeah, G and G will get cancelled out. So we have h equals to what? Okay, we have 2 times h multiplied by g by r is equal to r omega square. So if we take this 2g and r on other side, we get h equals to r square omega square divided by 2g. Okay, so option A is the answer. The work done, the work done to raise a mass m from the surface of Earth to height h, which is equal to radius of Earth is. Okay, so now we cannot use change in or work done against the gravity equals to mgh. Okay, we have to use the other formula, right? So work done is equal to what? Potential energy at height h minus potential energy, okay, at r, right? So potential energy at height h, we know it is minus of g times m into m divided by r plus h, minus potential energy on Earth's surface is minus of g times m multiplied by m divided by r. Okay, and then h is equal to how much? Radius of Earth. Okay, so in place of h, I will put r. Okay, so this is minus of, we can say, half of gmm upon r, because in denominator we have 2r, plus 1 gmm upon r. Okay, or you can say 1 minus half gmm upon r. So it is half gmm upon r. Okay, so which is the answer? And you can substitute gm equals to gr square whenever you want. Okay, so let's substitute that. So when you substitute that, you get what? It is equal to half of mgr, right? Option D. Next question. So at what height from the surface of Earth the gravitational potential and the value of g are minus 5.4 into 10 raised to 7 joules per kg and 6 meters per second squared respectively? take the radius of Earth equals to 6,400 kilometers. Okay, so they are asking at what height the gravitational potential, which is V is equal to this thing, okay, this one, and G is this much. So we know V is equal to minus of Gm upon R plus H, right? Okay. So they have given it in terms of acceleration due to gravity. That means we have to use other formula. So Gm equals to Gh into R plus H square. If we substitute that, we get it is minus of Gh multiplied by R plus H. Okay. And now we just have to substitute the values. Okay. So this is minus 5.4 multiplied by 10 raised to 7. It's equal to minus of Gh is 6 multiplied by R plus H. Okay. So this is 54 multiplied by 10 raised to 7 divided by 6. So how much is that? 9. 9 times 10 raised to 6. Okay. So R plus H equals to 9 multiplied by 10 raised to 6. How much is R? It is 6,400 kilometers. Okay, so R is 6,400 kilometers, or you can say 6.4 multiplied by 10 raised to 3 kilometers. Okay. And if you want to convert it into meters, so 1 kilometer is 10 raised to 3 meters. So we can write this in meters. So it will be 6.4 multiplied by 10 raised to 6 meters. Okay. So then we substitute that here and take it on other side. Okay, so that it gets subtracted from this number. So we get H equals to 9 multiplied by 10 raised to 6 minus 6.4 multiplied by 10 raised to 6. Okay, so how much is that? It will be 2.6 multiplied by 10 raised to 6 meters, or we can say 2,600 kilometers, right? Oh, you said option C? Good. All right, next question. An infinite number of bodies, each of mass 2 kg, are situated on x-axis at distances 1 meter, 2 meter, 4 meter, 8 meter respectively from origin. So there are infinite bodies and all of them have mass 2 kgs, 2 kg, okay, at distance 1 meter, 2 meter, 4 meter. There is nothing at 3 meter, 4 meter, 8 meters respectively. So m, so on and so forth. Then the resulting gravitational potential due to this system at the origin will be, okay, the resulting gravitational potential due to this system at the origin will be. So this is a good question. So what is gravitational potential? Minus of G multiplied by m upon r. Okay. So if there are n number of bodies, for them the gravitational potential will be equal to what? Net gravitational potential will be equal to sum of gravitational potential due to all of those bodies. Okay, so it is square root, sorry, minus of Gm upon R1. So R1 is 1, right? Okay, R1 is 1. Then we can take minus sign common actually and multiplied by Gm upon R2. R2 is 2 plus Gm divided by R3. R3 is 4 plus Gm upon R4. R4 is 8. Okay, so we can see what's happening here. This is a series. What kind of series? It is a geometric series. Okay, what is the ratio? So if this is first, if this is first term in the series, so if you multiply first term by half, you will get second term. Okay, then If you multiply that by half, you will get third term, so on and so forth, right? So this is a geometric series, and this will go till infinity. There are infinite such bodies. Okay. So what is sum of a geometrical series? Geometric series? It is a divided by 1 minus r. A is the first term, right? And r is the ratio. Okay. So it is equal to minus of gm, we can say. How much is m? M is 2 kg. Minus of g times m, let me write, multiplied by 1 upon 1 minus r. Okay. But this r is ratio, not distance. Okay. So minus gm, or g times 2, multiplied by 1 upon 1 minus half. Okay. So how much is that? This will be half. Take it into the numerator, it will become 2. 2 times 2 will be 4. Okay, so minus 4g is the answer. Option B. Right? Next question. Body of mass m is taken from Earth's surface to a height equal to twice the radius of the Earth. The change in potential energy of the body will be. Okay. So again now it's the similar question what we have seen, right? So how much is change in potential energy? So work done is equal to final potential energy minus initial potential energy. So minus of gmm divided by r plus h minus of minus gmm divided by r, because body is moved from Earth's surface to height h. So this is change in potential energy. Okay. So it is equal to minus of g times m multiplied by m divided by r plus, how much is height? Height is twice the radius r. Okay. So r plus 2r will give us 3r, plus we have gmm divided by r. Okay. So 1 minus 1 by 3 we can say, multiplied by gmm upon r. So it is 2 by 3, right? So it is 2 by 3 gmm upon r. And then we can substitute gm equals to gr square. So then this will be equal to 2 by 3, okay, multiplied by mgr, right? Yeah. Let's discuss next question. Particle of mass m situated at center of a spherical shell of same mass and radius a. The magnitude of gravitational potential at point situated at a by 2 distance from the center will be. So you have a shell. So due to this shell, there will be some gravitational potential. Okay. So how much would be gravitational potential due to shell? See, now here comes this concept that, okay, what is gravitational potential? It is work done per unit mass, right? It is work done per unit mass. Okay. So, okay, how much would be gravitational potential at this distance? There is a mass m situated at the center of spherical shell, and mass of the shell is also m. Okay. So now see, the gravitational potential inside the spherical shell is constant. Okay. Gravitational potential inside the spherical shell is constant. Okay, how why is that? Okay, what's the reason? So see, the field, gravitational field inside the shell is equal to 0. We had discussed that. Okay, the gravitational, see, it doesn't exert any gravitational force. Okay, shell doesn't exert any gravitational force on any mass which is kept inside it. Okay, the gravitational force is equal to 0. So if force is 0, okay, force is 0, what will be the work done to move a mass inside the shell? It will be 0. Yes, no. Okay, and that means how much would be difference between two points, sorry, potential energy of a mass at 2 points inside a shell. Since work done is 0, okay, the difference in potential energy is 0. Yes, no. Okay, so difference in potential energy is 0. Okay, and that means potential will be same. Okay, so let me explain this concept nicely once again if there is some confusion. So the question is, a particle of mass m is situated at the center of spherical shell, okay, of the same mass and radius a. Magnitude of gravitational potential at a point situated at a by 2 distance from the center will be. Okay, so we have this shell and its mass is m. There is another mass. There is another mass at the center of the shell, and that mass is also m. Okay, and now question is the magnitude of gravitational potential at a point situated at a by 2 distance from the shell, from the center. So this much distance is a. We want to find the potential here. Okay, at distance a by 2, right? At distance a by 2. Okay, so this much distance is a by 2. Now see, if I take a spherical shell, okay, then its mass can be anything. It doesn't matter. Now let's suppose there is a mass, small mass m inside that shell. So we know that the shell exerts no force on that mass, no gravitational force on that mass. Okay, so gravitational force on this mass is equal to 0, right? So therefore, now if I move this mass from, let's say, this position, let's call it A, to some other position B inside the shell. Since if mass is at position A or position B, there is no force acting on it due to the shell. Okay, so since there is no force, work done will be equal to 0. Okay, so work done to move it from A to B, A to B is equal to change in potential energy of that mass. Okay, so that is final potential energy minus the initial potential energy. And since work done is equal to 0, you can say potential energy at B is, okay, minus potential energy at A is equal to 0, or potential energy at B is equal to potential energy at A, right? Then see, now how do we define potential? Potential is work done per unit mass. Potential is work done per unit mass, right? So now, okay, so see, since potential energy at U is equal to potential energy at B, and it will be equal to potential energy on the surface of the shell. Okay, it will be equal to potential energy on surface of shell. You can consider this mass just over here. Okay, so therefore the potential inside shell due to shell is constant and it will be equal to what? So potential due to shell in interior points, at all interior points, will be equal to Gm, actually minus of Gm over radius of the shell. Okay, got it? Yes, no? Okay. This is potential due to shell. Okay, and there will be some potential due to this mass. How much will be that? So potential due to this mass will be equal to, okay, potential due to the mass m, which is at center. It is minus of Gm divided by a by 2, or it is minus of Gm, okay, 2Gm divided by a. So this is minus 2Gm upon a, and potential due to shell is minus Gm upon a. So it is minus of 3Gm upon a, right? But they are not considering the positive or negative sign. So it will be 3Gm divided by 8. This is the answer. Is it clear? Okay, good. All right. Let us see next question. This is similar question once again. A body of mass m is placed on Earth's surface, which is taken from Earth's surface to a height h equals to 3r. The change in gravitational potential energy is. So how much will be change in gravitational potential energy? So let's call it delta U, or work done we can say. It is equal to potential energy at final point Gmm divided by r plus h, and h is equal to 3r, minus potential energy at surface of Earth. Okay, this question is repeated many times, just values are changed, right? So it is equal to what? Minus of Gmm upon 4r plus Gmm divided by r. So it is 3/4 of Gmm upon r, or we can say it is 3/4 of mgr, right? Option C. Okay, good. You're doing this calculation very fast. Okay. Then let us see next question. A black hole is an object whose gravitational field is so strong that even light cannot escape from it. To what approximate radius would the Earth, okay, have to be compressed to be a black hole? All right. So if Earth becomes black hole, that means escape velocity is equal to what? Velocity of light, right? That is equal to square root of 2Gm divided by r. Okay. So here V will be equal to C. Okay, velocity of light. So light will not escape from Earth's surface. Okay. All right. So then what do we get? So we have to substitute these values. Oh, all these values and solve it. Okay. So it is 3 multiplied by 10 raised to 8, and we'll take square of that is equal to 2 times, this is 6.67 multiplied by 10 raised to minus 11. Okay, the value of G, multiplied by, this is 6 multiplied by 10 raised to 24 divided by R. Okay, they are asking us about R only. So it is, therefore R is equal to, will be 2 multiplied by 6.67 multiplied by 6 multiplied by 10 raised to 33. Okay, 24 minus 11, 33 divided by 9 multiplied by 10 raised to, so 10 raised to how much? 8 square, 16. Okay. Am I doing some mistake? 13. Sorry, sorry, sorry. Sorry, sorry. 13. Okay, 10 raised to 10 raised to 13. Right. Sorry. So then this is of the order of 10 raised to 17. You take it to numerator, it will become 10 raised to minus 17. Okay, 10 raised to minus 17 plus 13. 10 raised to minus 4, and 6 times 2 is 12. Okay, so this thing is of the order of 10 raised to 1, and 12 is of the order of 10 raised to 1. So we can, okay, yeah, so it will be of the order of 10 raised to 2, right? So 10 raised to 2 multiplied by 10 raised to minus 4. So answer will be 10 raised to minus 2 meters. Okay. Time period of a geostationary satellite is 24 hours. At a height 6 RE, RE is radius of Earth, from the surface of Earth. Time period of another satellite whose height is 2.5 RE from the surface will be. So they have given the time period of geostationary satellite is, it is 24 hours, we know that, and its height is 6 times RE. So T2 square is directly proportional to R2 cube, and T1 square is directly proportional to R1 cube. So now if we divide this first expression by the second expression, what can we say? We can say that T2 upon T1 square is equal to R2 upon R1 cube. Okay, so this is equal to what? R2 is 2.5 RE. We can substitute that 2.5 RE upon 6 RE. R1 is 6 RE, and we have cube of that. Okay, so this is T2 upon T1 square. Then RE and RE gets cancelled out. Okay, so the thing that I have done wrong is, this is the height of our Earth's surface. Okay, this is the height above the Earth's surface, and this is not the actual radius. So we know small r is equal to capital R plus h. Okay, so I thought it is actual radius. Okay, so I'm sorry. Yeah, so then it's simple. So it is 6 times of RE is the height. 6 times of RE is the height. So how much is the actual radius? So it is R plus H, right? So it is RE plus 6 RE. Okay. Radius of first one is RE plus 6 RE, and radius for the second one is RE plus 2.5 times RE, and you have cube of that. Okay. So it is RE plus 2.5 RE is 3.5 RE, 3.5 RE, and in denominator you have 6 plus 1 RE, that is 7 RE, and then you have cube of that. This is T2 by T1 square. Okay, so this RE and RE gets cancelled out. Then 3.5 upon 7 is 1 by 2. So you have 1 by 2 cube. Now you can take square root on both sides. So 1 by 2 cube is 1 by 8. And if you take square root, because this is T2 upon T1 square. So if you take square root, it will be how much? So it is 2 root 2. That's T2 upon T1. Now take T1 on other side. So you get T2 equals to T1 divided by 2 root 2. Okay. And T1 is how much? It is 24 hours. So it is 24 divided by 2 root 2 or 12 upon root 2, or you can say it is 6 root 2. Okay, so 6 root 2 is the answer, right? A remote sensing satellite of a remote sensing satellite of Earth revolves in a circular orbit at a height of 0.25 multiplied by 10 raised to 6 meters above the surface of Earth. If Earth's radius is 6.38 multiplied by 10 raised to 6 meters and g equals to 9.8 meters per second square, then the orbital speed of satellite is. So we know the formula for orbital speed of satellite. Okay, so v equals to square root of gm upon r, that is square root of gm upon r plus h. Small r is capital R plus h, and you are given that height is this much, then Earth's radius is this much, okay, and small g, g is equal to 9.8 meters per second square. So now what we can do is we can convert this gm in terms of g, right? So what do we get? The g r square divided by r plus h, and now there will be a lot of calculation in this, but we can solve it. So it is 9.8 multiplied by r square. So how much is r? R is 6.4. Okay, let's do round figure. 6.4 into 10 raised to 6. So 6.4 multiplied by 10 raised to 6, and that is square of that, divided by r plus h. So r plus h is 6.4 multiplied by 10 raised to 6, and h is 0.25 into 10 raised to 6. Okay, so plus 0.25 multiplied by 10 raised to 6. Okay, so we have r square, and square root of that will not touch this thing. We'll just take it outside. Okay, so what we get? We get 6.4 into 10 raised to 6 multiplied by square root of 9.8, and in denominator what do we have? We have 10 raised to 6, right? Square root of that is 10 raised to 3, so we can take it outside, and then 6.4 plus 0.25, so it is how much? 6.65. Okay, so 10 raised to 6 upon 10 raised to 3 is 10 raised to 3, and 9.8 divided by 6.65 will be, we can say round figure, it will be how much? This is 3 is to 2. Okay, near about 1.5 or something. So square root of that will be nearly, we can say 1.2. Okay, and if I am correct, so this will be greater than, yeah, it will be greater than 6.6. So I guess this will be the answer. Okay, can you check? So let's move on to the next question. Satellite S is moving in an elliptical orbit around the Earth. The mass of satellite is very small compared to mass of Earth. Then A, the linear momentum of S remains constant in magnitude. B, the acceleration of S is always directed towards the center of Earth. The angular momentum of S about the center of Earth changes in direction, but its magnitude remains constant. The total mechanical energy of S varies periodically with time. So which one is correct out of this? This is simple. There is a satellite S which is moving in elliptical orbit. Okay, so does the linear momentum of S remains constant in magnitude? So linear momentum is mass times velocity. No, very good. Because velocity changes. Okay, so if it is revolving in an elliptical orbit, so velocity is more when the satellite is closer to the Earth, and velocity will be less when it is away from Earth, right? So, since velocity changes, linear momentum is not constant in magnitude. The acceleration of S is always directed towards the center of Earth. This is true. Okay, so this should be the answer. But let's check the remaining two. Okay, the angular momentum of S about the center of Earth changes in direction, but its magnitude remains constant. So this is wrong because the angular momentum will remain constant in magnitude also. Okay, so we had discussed this when we discussed Kepler's laws. So there is second law. So law of areas. Okay, so law of areas is law of conservation of angular momentum actually. Okay, so angular momentum remains not only constant in magnitude, it remains constant in direction also, because it is under the action of a central force. So we had discussed this when we discussed the Kepler's laws. So angular momentum remains constant in magnitude as well as direction. So this is wrong, and total mechanical energy varies periodically with time. So again this is wrong. So will the total mechanical energy vary? Total mechanical energy will remain constant because there is no external force, right? So if it moves away, speed will decrease. Okay, its speed decreases, that means the kinetic energy will decrease. But what will happen? Its potential energy will increase. How? Because potential energy is what? Minus of gmm upon r plus h is the potential energy. That means as height increases, what will happen? This fraction will decrease, but it has got this negative sign. Okay, so it was more negative earlier, now it is becoming less negative, right? Fraction decreases, that means when it is closer, it was more negative, but when it goes away, it becomes less negative. That means the potential energy is actually increasing. Okay, so this one is also not true. The total energy remains constant, right? So option B is the answer. Let us see next question. A geostationary satellite is orbiting Earth at a height of 5r. That means its radius is r plus 5r, right? R plus h. Okay, so let's keep this in mind. Above the surface of Earth, r being the radius of Earth, time period of another satellite in hours at height of 2r from the surface of Earth is. Okay, so again this is simple. Okay, and I think the answer would be same. Right? See, so for first one, so T1 is equal to 24 hours. Okay, so we can say T2 upon T1 square is equal to R2 upon R1 cube. Okay, so R2 is equal to what? It is R plus 5R because height is 5R. So it is 6R. And R1 is how much? It is R plus 2R because height is 2R. Okay, so it is 3R. Actually, the other way around, because R2 is okay, R2 is 3R and R1 is 6R. Okay, so height of first one is 5R. So R1 is R plus 5R and R2 is R plus 2R, that is 3R. Okay, so then we have got 1 by 2 cube, and so this is just like the previous question. So 1 by 2 cube is 1 by 8. So it is T2 by T1 square. So therefore T2 upon T1 is square root of this, right? And therefore T2 is equal to what? T1 multiplied by square root of this thing. So square root of 1 by 8 is 1 upon 2 root 2. And T1 is 24 hours. Okay, so they have just changed the values, but it is same question. So 24 upon 2 root 2. 24 upon 2 is 12. 12 upon root 2 is 6 root 2. Right, 6 root 2 hours. So option C is the answer. If V is the escape velocity and VO is the sorry, if V is the escape velocity and VO is the orbital velocity of a satellite or orbit close to Earth's surface, then these are related by. So tell me, VO equals to root 2 VE, VO equals to VE, V equals to root 2 V naught, or V equals to root 2 times VO, VO or V naught. Option C or D. Option D, right? Option D is the answer. Okay, all right. Then the radii of circular orbits of two satellites A and B of the Earth are 4r and r respectively. If the speed of satellite A is 3v, then the speed of satellite B will be. So again, this is okay. They have asked same type of questions again and again. Okay, the radii of circular orbits of two satellites are 3r and r respectively. Okay, so let's say r1 is equal to 4r and r2 is equal to r, and we know the formula for speed. So speed is what? V equals to square root of gm over r. Okay, so v1 will be equal to square root of gm upon r1. So you solved it, very good. So v1 is square root of gm upon r1, v2 will be square root of gm upon r2, and dividing by that is equal to what? Multiplied by its reciprocal. So multiplying by r2 upon gm. So gm and gm will get cancelled out. Okay, so v1 upon v2 equals to what? Square root of r2 upon r1. So that is r2 is r, r1 is 4r, r and r gets cancelled. v1 upon v2 is square root of 1 by 4, that is 1 by 2. Okay, that means v2 equals to 2 times v1. Right, v2 equals to 2 times v1, and therefore v1 is 3v, so it is 6 times v. So option B is the answer. Let's see next question. A ball is dropped from a space sorry, a ball is dropped from a spacecraft. Okay, it is tongue twister. The ball is dropped from a spacecraft revolving around the Earth at a height of 120 km. What will happen to the ball? So there is a spacecraft which is revolving around the Earth at some height, and you drop a ball from that height. What will happen? It will fall down to the Earth gradually. It will go very far in the space. It will continue to move with the same speed along the original orbit of spacecraft. It will move with the same speed tangentially to the spacecraft. Tell me, ball and spacecraft both have same speed, right? And you are just releasing that ball. Okay, so it has natural tendency. This is Newton's first law. Okay, so it was moving in circular orbit earlier, so it is inside or outside of that a spacecraft, it has got same speed. Okay, and because of that, it will keep on moving with the same speed in same orbit, right? So this is an example of Newton's first law. Okay, right. Okay, so let's see next question. A satellite A of mass m is at a distance r from the center of Earth. Another satellite B of mass 2m is at distance 2r from Earth's center. Their time periods are in the ratio of. Okay, so what are the ratios of time periods? So ratios of radii are 1 is to 2. So we know T1 by T2 square equals to R1 by R2 cube. Or we can say, if we take square roots, so it is R1 by R2 raised to 3 by 2, right? So it is 1 by 2 raised to 3 by 2, 1 by 2 raised to 3 by 2, or it is 1 by 2 cube, which is 1 by 8, square root of that. So square root of 1 by 8, that is 1 upon 2 root 2. Okay, so it is 1 upon 2 root 2. So option D is the answer. Very simple. What about the mass? It doesn't depend on mass, right? Mass is there to confuse you. Okay. So see, formula for time period is 2 pi square root of r cube divided by gm. And this mass is not mass of satellite. Okay. This is mass of Earth. So time period doesn't depend on mass of satellite. It depends on mass of Earth. Okay. So it doesn't matter how much is the mass of satellite. Okay. It does not depend on mass. All right. So let's move on to the next question. A satellite of mass small m is orbiting the Earth of radius capital R at a height h from its surface. Total energy of the satellite in terms of GO, the value of acceleration due to gravity at the Earth's surface is. All right. So we know the formula for total energy. How much is total energy? It is minus half of GMM upon small r. And what is small r? It is r plus h, right? And they're asking how much is total energy in terms of GO. GO is the value of acceleration due to gravity at the Earth's surface. So now we have discussed this repeatedly. The trick to solve gravitational problems, most of the problems, is use GM. Remember this thing, GM is equal to what? G multiplied by R square. So here they are calling it G suffix O, GO or G naught, and it is equal to GH multiplied by R plus H square. Okay. So out of these two, this one is what we have to use because they are asking it in terms of acceleration due to gravity on Earth's surface. Okay. It is minus half of GM is GO multiplied by R square into M divided by R plus H. So in place of GM, I am substituting this. So is it matching with something? Any option? I guess option B, M G naught R square. Yes, it's option B. Right. So this is also simple. Okay. Next question. The additional kinetic energy to be provided to a satellite of mass m revolving around planet of mass capital M to transfer it from circular orbit of radius r1 to another of radius r2, where r2 is greater than r1 is. Okay, so now how can you find out that energy? So it's simple. See, there will be some total energy of satellite at uh, radius r1. So let's call it total energy at r1, or let's just call it total energy 1. Okay, it will be simple that way. So it is minus of gmm divided by r1. Then when it goes to the next height, okay, r2, sorry, the other radius r2, it will have total energy equal to what? Minus gmm divided by r2. So now the difference between these two total energies will be equal to the extra kinetic energy that has to be provided, right? So it has got total energy, some energy, okay, some energy now when it is revolving at radius r1. It will have some energy, some total energy when it revolves at radius r2. So the difference between these two energies is the extra kinetic energy that you have to give. Yes or no? So how much is the extra kinetic energy? It is final total energy minus initial total energy. So it is minus of gmm upon r2. This is final total energy minus of gmm upon r1. So this minus, this thing becomes plus. So you can say, you can take gmm common, and this one becomes positive. So you can write it as 1 upon r1 minus 1 upon r2. Okay, so option B is the answer. Next question. Two satellites of Earth, S1 and S2, are moving in same orbit. The mass of S1 is 4 times the mass of S2. Which one of the following statements is true? The potential energies of uh, Earth and satellite in the two cases are equal. So this is not true, because potential energy depends on mass. It is minus of gmm upon r. It depends on mass of the satellite. Okay, so Sanjay is saying option B. Let's check. S1 and S2 are moving with the same speed. This must be true because they are moving in same orbit, right? So yes, this is true. Option B. Okay. So then the kinetic energies of two satellites are equal. So kinetic energies of two satellites cannot be equal because their masses are not equal. Okay, their masses are different. Okay. So speed is same, but kinetic energy is half of m into v square. So it depends on mass. Speed is same, but mass is different. So kinetic energies are different. Time period of S1 is 4 times that of S2. So we have discussed this earlier. The time period does not depend on mass of the satellite. Okay, it is independent of mass. So this is also wrong. So option B is true. Okay, option B is correct. For a satellite moving in an orbit around the Earth, the ratio of kinetic energy to potential energy is. So what is the ratio of kinetic energy to potential energy? So this is very simple. We have discussed this. Tell me. Kinetic energy is half of gmm upon r. Potential energy is minus of gmm upon r. If you take the ratio, you will get ke upon p equals to minus half. And if you just want the magnitude, then it is half. Option A. Right. So earlier you said C. Okay. Anyways, so A is the answer, right? Okay. Next question. The satellite of mass m is moving around the Earth in circular orbit with velocity v. What will be its total energy? So we know that total energy is equal to minus of kinetic energy, right? We know total energy is minus of kinetic energy. It is minus of half mv square. Option D. Okay, so this is simple. So see, now we have to memorize these things. What is the relation between total energy, potential energy, kinetic energy, and binding energy? Okay. Next question. The mean radius of Earth is r. Its angular speed on its own axis is omega, and the acceleration due to gravity at Earth's surface is g. What will be the radius of orbit of a geostationary satellite? Okay, so angular speed of Earth is omega and acceleration due to gravity on Earth's surface is g. What will be the radius of orbit of geostationary satellite? This is the question. Okay, so let's suppose radius is small r. Okay, so now uh, okay, so now what can we say that okay, for revolution of satellite, the centripetal force is provided by the gravitational force, right? So FCP is equal to GMM upon r square. Mean radius of Earth is r. The angular speed on own axis is omega, and uh, yeah, so we can use this formula, right? So then, what is FCP? The centripetal force. It is mv square upon r, or we actually omega is given, so we should use m r omega square is gmm divided by r square, right? Okay, and then this m and m gets cancelled out, so we get r cube is equal to gm divided by omega square. Okay, and therefore r is equal to square root of, sorry, cube root of this thing, gm upon omega square. Okay, and then we can substitute in place of gm or regular trick. So gm is equal to what? Gr square. Okay, so if you substitute that, gr square upon omega square, I'm sorry, so here it's cube root of this, right? Okay, so I have put the bracket, but I didn't take cube root. So r cube is gm upon omega square. R is equal to what? Cube root of that. Okay, so you have gr square upon omega square and cube root of that. Okay, so it's option A, option A or option B? Option A, right?